A very good morning to all the participants and our distinguished speaker. I welcome the wonderful audience for today's talk 4 of webinar series on electron microscopy titled Advanced Electron Microscopy Techniques for Magnetic Nanostructures Characterization. I begin with an overview of CEF, IIT Bombay, which was inaugurated by our late ex-Prime Minister Shri Morarji Desai. Instrumental methods of analysis form an indispensable aspect of any research and development program. The Department of Science and Technology set up the sophisticated analytical instrument facility in different parts of the country. The main objective of setting up these facilities was to provide guidance in acquisition of data using sophisticated instruments. Professor Anil Kottantharial is currently heading our CRNTS department. CEF IIT Bombay has several analytical instruments and provides measurement services to IIT Bombay users and to its users from other colleges, universities, national laboratories, and various industries as well. The current slide shows the list of instruments funded by DST, in which 2 of the electron microscopes have been highlighted. The one at the bottom is an upcoming facility, a dual beam FIB, which will be installed soon. The next slide shows the list of instruments which come under the central facility funded by IIT Bombay. Today, we are going to highlight the 3 transmission electron microscopes. One of them is a conventional TEM and the other 2 are field emission gun instruments with different analytical capabilities, like the 200 kV FEC TEM has energy dispersive spectrometer attachment with it, and 300 kV TEM has EDS and electron energy loss spectrometer as well. All the TEMs are located at CEF CRNTS. We have created a LinkedIn account for CEF IIT Bombay. We would be happy to connect with you through this mode too. This is the brochure for webinar series on electron microscopy, which is uploaded to this LinkedIn account. Following slide shows the staff at CEF CRNTS. We would be happy to welcome you at CEF and help you with the sample analysis. Talk 4 in the webinar series on electron microscopy is on advanced electron microscopy techniques for magnetic nanostructures characterization and will be given shortly by Dr. Jyotikanta Mohapatra. It is a great pleasure for me to welcome Dr. Jyotikanta Mohapatra, who joined the Department of Physics at the University of Texas, Arlington as postdoctoral fellow on November 2015 after completing his PhD from CRNTS Department, IIT Bombay. He has been a meticulous TA for FEC TEM 200 kV laboratory. He is currently serving as a research assistant professor and performing research in a broad nanomaterial portfolio, which includes nanostructured magnetic materials, 2D materials with emerging physical properties, and functional oxides for electrocatalysis applications. He has published more than 45 research articles, 3 patents, and 1 book chapter in this field. Several of his research articles are featured on the journal's cover page and the conference web page. We are sure that this talk will enlighten the knowledge of the upcoming researchers in the field of electron microscopy and encourage them to use electron microscopes. Question and answers to be posted in the question and answer box. Questions with the participants' names only will be answered. So let us commence today's webinar on electron microscopy techniques for magnetic nanostructures characterization. Over to you, Dr. Jyotikanta.
Thank you, Mayra, for the nice introduction. First of all, I'd like to thank the organizing committee, Aradhana, for inviting me to give the talk. And also, I would like to thank HOD CRNTS for organizing such a nice workshop, particularly on TM microscopy, which is one of the tools I have been using from 2009 to today to characterize different kind of nanostructure material, including magnetic nanostructure material. The today talk I am going to here present a small piece of my research work. Uh, Although I am not as electron microscopy specialist, I will try to give you some of flavor how the microscopic electron microscopy can be used to characterize low dimensional magnetic material. Uh, so here is outline of my talk. First, I will give you a basic introduction about magnetic material, particularly low dimensional ferromagnetic material. I'll talk finite size effect when we are controlling the particle size of magnetic nanoparticle, how the properties will change. Then I'll talk about thermal instability in a finite particle, which is one of the issue in ferromagnetic material, but that also sometimes advantage for particular application like MRI and hypothermia. I will give a few examples on that. Then I will talk about shape anisotropy and diameter effect. This part mainly to design hard magnetic material. So after that, I will some of my experimental results I will discuss relationship between microstructure and magnetic properties. Then I took some of the example where Lorentz TEM used to characterize domain structure in magnetic nanoparticles. Then I will talk a the coherent magnetization reversal in ultra thin nanowire assemblies. This is very interesting one. I'll discuss. I'll tell why it is interesting. Then finally, I will conclude my talk. Okay, so so when we talk about magnetic material, so basically it's comes the picture is here. It's very clear where we can find magnetic material. So in car there are 24 places where we can find permanent magnet. So the sophisticated diagnosis instrument like MRI, it's need permanent magnet. A renewable energy source like windmill, it also need permanent magnet. A simple microwave also it needs permanent magnet. We cannot realize a laptop computer without permanent magnet. Even the today kids who is born, they also needs magnetic toy. So magnet is everywhere. It's critical for many modern application. Okay, so this is these are application here I am highlighting. All are permanent magnet. Okay, these we called as bulk magnetic. Here in all these application we use bulk magnetic material. So this is a new when the size of the particle goes to nanoscale, they exhibits different kind of properties. How why they exhibits I will explain in the next slide, and that leads some kind of important new technology like hypothermia. So it's alternative to cancer, alternative therapeutic tool to treat cancer. It can be used as a contrast agent to detect primary stage of cancer. Since this we are talking about nanoparticle, so if each particle behaves as a single domain, each particle we treat as a single domain. So single domain, either it will be aligned as spin up and spin down. So then each particle can be treated as one domain. So in that case, we can think about high density memory device, storage device. So there are lots of application, particularly nanostructure magnetic material. So before going to the low dimensional magnetic material, I want to first emphasize here from where that magnetic properties is coming. Okay, so it's here I highlighted three of the. One is the intrinsic properties. Each material, they will have magnetic moment. It's mainly comes from the spins, electron spins. Then when you put a spin in a uh, uh, crystal system, so it will have crystalline anisotropy. That's also intrinsic properties. And this ordering, the ferromagnetic ordering, that exists up to a certain point. So that also a intrinsic parameter. All these are intrinsic parameter. It's but there are some of the magnetic uh, uh, microstructure. These will not change with the microstructure, but if we'll change the microstructure like crystallinity, morphology, particle size, uniformity, magnetic length scale, grain interaction, so these are the extrinsic properties can be tuned. One is the remanence, coercivity, and energy product. What is this? This is a typical magnetization loop for two kind of material. One is the hard, one is the soft. So what is hard? The material which suppose we apply a high magnetic field, it got saturation, magnetization. To completely demagnetize the saturation magnetization, we need to apply a reverse field. The amount of the field we need to completely demagnetize the material is known as the coercivity. Okay. The material which exhibits high coercivity, they are known as hard magnetic material, and they are ideal candidate for permanent magnet design. And the material which exhibits low coercivity, that they are known as soft magnetic material. Mainly all the ferrites, they are soft magnetic material. In nanoscale, the ferrite, if we'll decrease the size, they will exhibit zero coercivity. I'll talk in the next slide. So, but for permanent magnet design, we need material with high coercivity and high remanence. That's why rare earth compounds like neodymium, iron, boron, they are known as a strong magnet because they exhibit strong spin orbit interaction. So here is the how I will identify a permanent magnet strength. So here from that image curve, if we'll convert the image curve to the BH curve, the rectangular area under the BH curve, the maximum area under the BH curve is known as the energy product. A magnetic material which give high BH max is ideal candidate for high strength permanent magnet design. Okay, so from where those coercivity, what is the origin of coercivity? So origin of the coercivity is the anisotropy. So from where this anisotropy is coming? Anisotropy comes from, one is the magnetocrystalline anisotropy. When we put the spin in a crystalline structure, so they will depends on the crystalline structure, they will have a preferential orientation. Like here I talk about HCP. HCP, the spin will be it has a preferred orientation is the C-axis. like here L10F tetragonal FEPT structure, it has the C axis is the EG axis. Okay, so these are the particularly related to the material. Okay, but if we need to further take introduce some outside source, so shape anisotropy is one of the source. If we'll design, let's say, cobalt HCP cobalt nanorod shape, we can have we can have both shape anisotropy and magnetocrystalline anisotropy together, and we can have a giant anisotropy. And then based on the high giant anisotropy, we can develop high coercivity, which is required for permanent magnet design. Okay, so this is the size dependent coercivity. This slide is saying if we'll control the particle size of any ferromagnetic material, let's say from multi-domain structure, which is usually above it depends on the mainly on anisotropy, but usually it's above 100 nanometer. So if it decrease, the coercivity will increase, and exactly at the single domain, so we can have high coercivity, because in single domain you can see that this picture, so the spins are all aligned in same direction. So if we'll apply external magnetic field, they will coherently rotate. And because of the coherent rotation, they needs high field to reverse completely. In that case, we can have high coercivity. If we'll further decrease the particle size, so the anisotropy energy is directly proportional to the volume of the particle. So if we'll decrease, so basically we are decreasing the anisotropy. So then when the anisotropy energy is equivalent to the thermal energy, so they will be no more ferromagnetic. They will fall in this region. That's called the superparamagnetic region. Here, because of the thermal fluctuation, the spins will, although we inside we have a ferromagnetic ordering, but particle itself will fluctuate because of the thermal energy. So if you apply the magnetic field, you can spontaneously magnetize them. When you will remove, so they instantly they will go to the random state and lose the magnetic moment. However, here once we magnetize them, they will retain the ferromagnetic alignment, and that's why the material in this region is ideal for designing super strong permanent magnet, and the material in the superparamagnetic region, they are ideal for biomedical application. Some biomedical application like hypothermia, even drug delivery, MRI imaging, where we whenever we need, we will apply the magnetic field, and once we remove, they will demagnetize by themselves, so that there will be no agglomeration. Okay, so here is what I did during my PhD. Even we are doing right, my group currently doing here. So we basically control it's one of the example where we precisely control the size of the iron oxide nanoparticle from 4 nanometer to 32 nanometer. Okay, and thanks to the chemical approach we are adopting, that's a thermal decomposition approach, which yield highly monodisperse nanoparticle. We have control from 4 nanometer to 32 nanometer, but we can go further also. Here, how with the size, the magnetic properties is changing. Here you can see, as we increase the size of the particle, these are some of data taken from my paper, and some of the data taken from the literature. You can see as we increase the size of the particle, the saturation magnetization is increasing. Why it is increasing? Because the nanoparticle, it's when we are decreasing the size, the effective surface area, or we can say the surface to volume ratio, is increasing. And the surface in most of the nanostructure material, surface will have defect state because of coordination with the surfactant, and also because of different facets. I'll talk in some of the slides how the facet will affect the magnetic properties. So it's mainly due to the defects. As we decrease the size, the surface defect will increase. In this magnetic system, here the surface defect is the surface spin disorder. So since that increase, so the saturation magnetization, we have a tunability over the saturation magnetization. Depending on the requirement where we need a particular saturation magnetization value particle, we can select the size and use it as per the requirement. And this is I told when we control the size, we can go from the ferromagnetic state to superparamagnetic state. Superparamagnetic is a where the magnetic spin fluctuation will be there. So this is a zero field magnetization plot. We usually record it to see where is the transition is happening from ferromagnetic to superparamagnetic, and the peak, the peak of the GFC, let's say this gray color plot, the peak is known as the blocking temperature. That's the transition temperature below which the particle will be blocked. That means it will be in one of the ferromagnetic state, and above it will be in superparamagnetic state. So you can see as we increase the particle size, the peak is shifting towards the higher temperature. Okay, so that's and another interesting you can see feature you can see in the 24 nanometer particle. Okay, so there is this blocking behavior like this peak is not visible in 24 nanometer size. Okay, rather we have a transition, a very sharp transition at temperature around 120 Kelvin, and that transition is also that particular transition you can also see in 20 nanometer, the blue curve. Okay, that's a characteristic transition of this particular material. That's the Fe3O4 magnetite. That's only appear when the material is highly stoichiometric, means there is no defect. So that we can say here the I was telling, as we decrease the magnetization decrease due to the defect, and it saturate, and the saturate in the above 20 nanometer, the saturation magnetization it's nearly constant. It's because they are defect free and they are highly stoichiometric. So here is the same trend. I took some of the data took data from some of the reference paper. So you can see with increase of the size, the blocking temperature, that's the superparamagnetic transition temperature, it's linearly following a linear relationship. It's increase with increase of particle size, and here the relaxation time. So I mentioned these will exhibit superparamagnetic relaxation. So we calculate the superparamagnetic in solution form. We calculate the effective relaxation time, applying AC magnetic field. We determine the Brownian relaxation time. In solution, the particle can also rotate, exhibits Brownian motion, and we also calculate the nil relaxation time. So the nil relaxation time, the green curve, it's increase monotonously with the increase of the particle size. So, and this is the measurement frequency of the instrument, of the instrument we are using to determine the relaxation time. So the particle size where the nil relaxation time is matching with the measuring reverse of the frequency, that's the measuring time. So that's is the size below which the particle will be superparamagnetic at room temperature, and above will be ferromagnetic. And we identify here, so if we will go beyond 16, so in a particularly iron oxide case, they will be superparamagnetic, and above they will be ferromagnetic. Okay, I talked in the previous slide about surface spin defect. It's also known as spin canting effect. Okay, so here is two different particle. One is of 20 nanometer, another is of 5 nanometer. Okay, so it's not only surface defect, there will be internal defect also. Okay, you can see this is the high resolution TEM image. It's showing the particle is highly crystalline. It's a good crystalline, and it's single crystal. I took the FFT from the whole region. You can see it's exhibiting. There is no. It's a 100 zone axis. And these are the spots are very prominent. So there is no secondary spots. That's indicating that the particle is single crystalline. Here, although it's showing the same hexagonal symmetry, the F50 pattern, but the spots you can't see. Here you can see the second order. Okay, here you cannot see the second order. Okay, so in addition, if we'll see the high resolution TEM, the lattice fringes are not clear here. Okay, so that's because the particle, in addition to the surface defect, the particle itself having a internal defect. Okay, the spin canting effect, it's not only in the surface but also internal inside. That is the reason why the magnetization is sharply decreasing. It's not a linear relationship. It's rather decreasing sharply when in the superparamagnetic region, particularly below 16. So that's because when we are decreasing, we are also introducing more and more internal defects, spin disorder. Okay, so can we control the spin disorder? That's one of the since we are observing below 16 nanometer, there will be always spin canting. Can we control? The question is now. Yes, we can control. What we did here, we control the shape anisotropic. We modulate the shape of the nanoparticle from spherical to octahedral, cube, multiport structure, nanorod, nanoair. Okay, so we modulate the synthesis approach to synthesize different morphology. Why we modulate this one, I'll tell. So in spherical nanoparticle, although the TEM shows the particle is looks like spherical morphology. In reality, but we cannot construct a sphere by because these are, if we'll consider the unit cell is cubic unit cell. With the cubic unit cell, we cannot construct a particle of perfectly spherical morphology. So here, if we did those results, I haven't put here. We did in the simulation. We found that so this spherical nanoparticle will have multiple facets. It will end with n number of facets. However, if it is a octahedral, it will have only couple of the facets. And if it is cube, how many facets? It's just very few number of facets. And if it is rod, the face we are decreasing the facets. So by controlling the facets, we control the magnetic properties. We have controlled the spin, surface spin disorder. Okay. Another point logic is here. So here in anisotropic morphology, the growth is happening in preferential orientation. Okay, that's is giving better symmetry and reducing the surface spin canting effect. Here you can see, so this is the gray one is the multipode, or sphere one is the red one is the sphere. They are showing, the GFC is showing typical blocking distribution, as I mentioned in the previous slide. However, you can see the rod, where octahedral, cube, all they have a transition at around temperature 120. Okay, which saying that by controlling the morphology, we can control the surface defect, surface spin canting, and that also you can see here. If we will compare the saturation magnetization, the octahedral cube, they are giving magnetization value close to the bulk magnetization value. Bulk is around 84, and we are getting exactly same. So in this with the help of TEM characterization and with some simulation, we not only confirm that by modulating the safe morphology of magnetic nanoparticle, we can control the magnetic properties. Okay, so once we have control over the magnetic properties, we study some of application. We did the hypothermia properties. We only measure the temperature profile. Here you can see this is the measurement condition. We measure in AC magnetic field with current of 310 ampere and frequency 267 kilohertz. So if you will see, compared to all other structure, nanowire, nanorod, even the cubes, octahedral, they are giving high, good heating activity. And when you calculate the SR is it's calculated from slope of the linear portion of the temperature profile. The SR it's a quantification how efficient is your material in producing heat. So you can see the nanorod, nanowire, they are very good. Although we got high magnetization in octahedral and cube, but nanorod, nanowire are very good because he, in addition to their magnetization, here there is another kind of heating effect we found. We found that because of the safe anisotropy, they are exhibiting ferromagnetic properties. You can see we took the minor lobe of a spherical nanoparticle and equivalent material volume of nanorod. You can see here is they are exhibiting under this is AC minor lobes taken the same frequency, I think. So it's showing loop opening. So that's indicating that in case of nanorod, we will have two different synergistic heating mechanism. One is due to the hysteresis loss. Hysteresis loss means there is one particle you are applying, giving AC magnetic field. The magnetization is you are magnetizing, demagnetizing. Because of the magnetization reversal, one kind of heating, that's a susceptibility. Another one is the hysteresis. Because of the combine, we found high heating efficiency. We also check here the MRI contrast properties. These material are very good for detecting but some particular type of cancer, primary stage of the cancer. So since we have a very good control over the morphology and size, so we thought of checking the relaxivity. And here you can see compared to the sphere, this one, the dark contrast is very good in case of nanorod, and when you calculate the relaxivity is very good for the nanorod. Okay, so not only by controlling the morphology, we retain the surface magnetism, we improve the effective magnetic properties of the material. We also found that they are very useful for the biomedical application. To understand why the rod is giving high heating, high MRI contrast properties, we did COMSOL multiphysics simulation. You can see the induced local magnetic field, which play important role in MRI contrast imaging, is very strong for the nanorod in compared to the nanoparticle. Here you can see with the, as we go away from the surface of the nano particle, so the field strength is strong for the nanorod. This paper published in nanoscale, and also highlighted as front cover page of that issue. So another kind of another example is here is the exchange couple magnetic nanoparticle. We work here on exchange couple magnetic nanostructure to basically develop to improve the saturation magnetization. So here is one of the example. This work is a collaboration work. So here we synthesized iron oxide nanoparticle. Then we coat the iron oxide nanoparticle with iron oxide itself. We use this as a seed. Then we put a secondary coat. And in figure C, we instead of iron oxide, figure C, we put zinc, manganese, iron ferrite. It's a mixed ferrite. So this size in figure C and figure C, particle size is average particle size is nearly same. So only what we are doing, we are changing the cell. Here it is zinc ferrite, and the figure zinc, manganese, ferrite, mixed ferrite, and here in figure D it's manganese, iron, ferrite. Okay, so to confirm this core cell structure, we did took the high resolution TM image, although it's giving an indication that it's having some lattice change, but since the structure is these are all this both the core and cell, they are spinel cubic structure, so there is no appreciable change. Okay, so we did the elemental, we collected the EDS spectra. You can see here it's showing the iron. The copper is coming from the copper grid itself, and here it's showing manganese, the presence of manganese, zinc, and iron. It's indicating that so the sample is having iron, manganese, and zinc. But where is the manganese? Whether it is cell, where is the zinc? Whether it is cell? So that's not confirmed from here. We did magnetic measurement to see how it's improving or changing the magnetic properties, but it's not a direct evidence. So what we did, we took the yields mapping. So here it's a yields mapping tech. From this is the STM image. So from 5 different locations, the elemental mapping is taken. You can see here. Okay, so spot 1 and spot 5, it's showing the presence of manganese. You can see here. Okay, so here the yields mapping further confirm that the cell is of the cell is having giving a different construct, green contrast that belongs to the manganese. So it's by using the yields mapping, we confirm that it's a core cell morphology. Okay, now I will talk about some of the advanced technique to characterize domain structure, to know the internal structure of magnetic nanoparticle, whether it is a single domain. If it is a single domain, how we'll know that I will talk. I haven't used this technique myself, but we have one collaborator who is doing, we are sending, and they're doing the Lorentz transmission electron microscopy characterization. I'll show some of my result, and I will also take in some of data from the literature. I'll explain here. So it's the design is similar. The Lorentz transmission electron microscope design is similar to the TEM. The only difference is here. So the lens is here is a Lorentz lens. So there are different mode of imaging. One is focal mode. Here, if you consider this is the sample, it's here. This is the spin up, and this is the spin down. So when electron beam pass through it, magnetic domain, depending on the magnetization, the induction field, the electron will scatter. Okay, in this mode, the if will block one of the let's say the beam coming from this domain, will block that beam using aperture, then that particular domain will appear in the dark field imaging, will appear as dark contrast. If we will block this one, if we will open it, it will come as a bright contrast. Another one is a Fresnel mode. So it's both there is no aperture, So basically both the beam interfere each other, they will form an image. So if the beam is focused, so there will be no difference in the domain. Okay, so to identify the domain, so we need to slightly overfocus the beam. So in overfocus, so the domain wall will come as dark contrast. If it is under focus, then domain wall will appear as a bright contrast. So the main difference between the focal mode and Fresnel mode, in focal mode, the domain, the contrast come from the domain. In Fresnel mode, the contrast come from the domain wall. You can see the domain wall. So this is two type of mode. So if you want to study more about the internal structure, we can use the off-axis electron holograph. Off-axis electron holograph, here the sample, in the previous case, sample is completely inserted. So in off-axis electron holograph case, this half of the sample is inserted here. So basically, we have the principal beam here and the scattering beam here. Okay, both will interfere. The interference of both the beam will give the since there will be a phase difference between both the beam, the interference will produce a holograph. That hologram will tell the domain structure, whether it is a single domain, whether it is a multi-domain, how what is the domain structure. Is it a coherent domain structure, or it's a vortex? So that it will tell. So here this is same iron oxide nanoparticle. It's I took from this literature. So it's of around 100 nanometer particle. So here they study the thermomagnetic behavior of iron oxide nanoparticle. So so you can see the holograph is electron holograph is yeah, yes, electron holograph is saying that the flux line, these are the flux line here they are forming a vortex. Okay, so they are forming a vortex, and here the particle, although they are close to the theoretical domain limit, but they are not single domain. They are consist of two vortex, one vortex here, one vortex here. Okay, that's at the room temperature. When they heat it at high temperature, so the spin, the flux lines, although they are coming, it looks like they're coming here to here, but if you'll go to the outer periphery, they are close. Okay, so they are still in vortex stage. And this case, it's in the high temperature. Now it looks like single domain. Okay, because the spins is coming from here, the flux line is going from here to here. Okay, so but if we'll see the edge is not uniform, this side. Okay, so there is a gradient, there is a the magnetization different. The magnetization different from here, this region to this region. Okay, that magnetization different is saying that it's not, although it looks like a single domain, it's not a single domain. When they decrease the temperature, now it's come back to again the vortex stage. So we can identify it, but it's an example, but sometimes it's very important to know to explain the magnetic properties. So here the thermomagnetic behavior, this similar sample, this guy they study below TC and above TC. So the TC of iron oxide is around 580 degrees centigrade. You can see as the TC, as they approach the TC, so you know TC, above the TC, the material will lose the ferromagnetic ordering. You can see there is no flux line. Okay, so all these cases they are forming the vortex. Okay, so I will give tell you one of our example. We work here on hard magnetic material. We adopted different approach to improve the coercivity, to use the material for permanent magnet design. So here we synthesized cobalt nanowire, HCP cobalt nanowire, and we align them under magnetic field. Uh, After alignment, you can see the material is giving very high coercivity, of 12.5 kiloostrel. This is the record high till it found in cobalt system. The theoretical anisotropy, effective anisotropy is 16.5. We almost close to the theoretical value, and we calculate the energy product of the sample. The energy product we are getting is around 40 MGoE, which is a good number. That's indicating that the material can be useful for permanent magnet design. So this nanowire is we are having C-axis along the nanowire. That is giving enhancing the effective anisotropy, and they are single domain. In the one of the beginning slide I mentioned, in the single domain regime, if we can develop high anisotropy, so we can have high coercivity. Because of that, we are able to develop a record high coercivity in transition metal system. This material can be an alternative to a rare earth permanent magnet, which most of the rare earth elements are rare earth. So if we have a transition metal replacement, so that's good, and we did that. Okay, so I will conclude my talk. Several new methodologies we have designed to prepare nanomagnet. Several new insight we have observed in low dimensional magnetic system, but it's not finished. There much more we need to know. For example, spin ordering in 2D ferromagnets, how the spin ordering will be, that's nobody know. So that's one of the maybe sophisticated electron microscopy can reveal in different material how the spin ordering is happening. Simple way still way of achieving new magnetic nanostructure still we need for commercial application. Some of the basic fundamental I haven't explained in detail. So if someone interested, please refer this book. And this is one of the review article recently we published. It's a hard and semi-hard magnetic material based on cobalt alloy. Why we need to consider cobalt alloy? That's instead of rare earth compounds like neodymium and boron. That's we emphasize in this review article. This is one of the review article published in recently. It's talk about inductive thermal effect in ferrite nanoparticle, the size effect, morphology, composition effect, and intra and interparticle interaction, how useful for biomedical application. I would like to thanks University Arlington, uh, University of Texas Arlington, and UTA Characterization Center for all the facility, the TM facility I use to characterize this material, and also some of initial part of my talk, those TM characterization is done in CRNTS IIT Bombay. I would like to thank you. Thank you very much.
Thank you, Dr. Jyoti Kanta, for an interesting talk. Let's begin the question and answer round. The first question of today's talk is by Dr. Rohini Mandare. She wants to ask, if we have synthesized nanoparticles but not uniformly magnetic nanoparticles, how can we separate or isolate magnetic particles?
It's a not non-uniform magnetic nanoparticle. Okay, this if you have a particle, they are getting agglomerated. You need to do the better functionalization so that they will not be agglomerated. Use some long chain surfactant like oleamine, oleic acid. That will help to avoid the agglomeration. But the other part she is mentioning, if they are not uniformly magnetic, you cannot, if you have a particle, you cannot break it. Okay, agglomeration you can break it by using powerful sonicator. You can break the agglomeration, but you cannot break the particle. To break the particle, you need to do the ball milling. So the correct answer is I would suggest do better surface functionalization.
Okay, thank you, Dr. Jyoti Kanta. The second question is by Dr. Saptarshi Maiti. He wants to know what is the effect of type of magnetic nanoparticles on the spin disorder phenomena apart from the size of the nanoparticles.
Okay, it depends on the type of magnetic nanoparticle is. If you will see, when I talk about surface spin disorder, those particles mainly those are ferrite. Okay, when I talk about cobalt nanowire, there was no surface spin disorder, and the TEM electron holograph is saying that the particle is highly crystalline and single domain. So the single domain. So and the reversal mechanism is coherent. Okay, so if you have defect, we would not have that coherent reversal. So it depends on the type of material is, because ferrites, for example, ferrite it's a antiferromagnetic. The sublattice, it consists of two sublattices, and the sublattices are antiferromagnetic, exhibits antiferromagnetic arrangement. Because of that, most of the ferrite, they exhibits high surface spin disorder when we decrease the size. But the same effect you may not find if you will go to the metallic nanoparticle like cobalt, nickel. It depends. If it's a 2D material, you will have, because of the high surface to volume ratio, you will have more prominent surface spin disorder. It depends on the material, it depends on the morphology. Yes.
The next question is by Tangadurai. Usually, at high temperature, magnetism is lost. How could these materials retain magnetic domains at 500 degrees Celsius or 600 degrees Celsius?
Yeah, the domain structure will maintain up to their TC. Okay, TC is the Curie temperature. Up to the Curie temperature, you will have the ferromagnetic ordering. Okay, so it will retain. Above the Curie temperature, we will lose the ferromagnetic ordering. If you'll see in one of the slide, that electron holograph, it's explained that when they went to high temperature above the TC, so there was no flux line. So below Tc, you will have the ferromagnetic ordering. If you will have the ferromagnetic ordering, you will have the corresponding flux line.
Thank you, Dr. Jyotikanta. On behalf of CRNTS, I would like to thank Dr. Jyotikanta Mohapatra for an interesting talk on advanced electron microscopy techniques for magnetic nanostructure characterization. We are really grateful to Dr. Jyotikanta for answering questions asked by the participants. I would also like to thank our head, Professor Anil Kotantarail, for his continuous support in this webinar series. And last but not the least, I thank all the participants for attending this webinar and making this event successful. A link for the feedback form is shared in the question and answer section. Please fill the form. Your valuable inputs are important to us. The registration link for the next webinar is now open on our website and will be accessible for the next 2 days till 21st of August. The upcoming talk is on basics of EDS and WDS analysis by Mr. Mangesh Kulkarni, Country Manager with India Office of Oxford Instruments, United Kingdom. I request you all to join us for our next talk. Once again, thank you all for making the webinar successful. Stay healthy and safe. Jai Hind.